Okay, off we go. Let's see. Before we get into the math, attendance quiz, attendance code, all that. Also, apologies for the temperature in here. I think it was Friday or sometime very recently. For the umpteenth time this semester, somebody bumped into the thermostat, knocked it off, disconnected it, etc. And it seems now to be stuck in heat mode. So I don't know what's going on there. Anyway, I've turned it off. I opened a window. If y'all want to open other windows, feel free. You get no argument from me. Anyway, here we go. Okay, so let's see. Last time, so we were talking about this idea of flux. Now, super quick reminder, because we've already covered this page, but the big idea of flux is that it allows you to compute certain flow rates, right? How much fluid per unit time, either in the sense of volume per unit time, or mass per unit time, whatever, depending on how you set up the vector field. But our formula depends on certain assumptions, namely that the vector field is constant and that the surface is flat. Okay, so what we talked about is how to generalize that to a non-constant vector field and a non-flat surface. And, we came up with this pretty reasonable idea of chopping it up into a bunch of little pieces, right? And arguing that the flux through the whole is the sum of the fluxes through the parts. And we did have to worry about this idea of an orientation, right? So which direction through the surface we're going to call the positive direction, right? So we had to kind of add that in. And with that done, it's a pretty straightforward calculation. Whole is the sum of the parts. And on each piece, we have a basically flat surface with a basically constant vector field, and therefore use the old formula. And then the last thing we did is we talked about this rewriting in ds as ds vector, like so. And I argue that this is very, very analogous to a similar relationship that we talked about for vector line integrals. And the punchline is this ds vector just encapsulates two things. What is the orientation and the size of the relevant piece of the domain? And now here, of course, size means surface area. With vector line integrals, size means length. So different geometry for the different context, of course. Okay, so that's where we left off. So here's the good news. We're actually in pretty good shape to go ahead and write down a formula. We have actually already developed all the machinery that we need. Let's look at what we have on the screen here. Everything on the screen is stuff that we've already talked about at one time or another. So in the last section, we talked about all this stuff. If you parameterize a surface, you can talk about the relationship between input size and output size as the magnitude of this capital N vector thing. Okay, that's our stretching factor. And then these equations down here we just wrote down on the previous page. So this is all just recopy for convenience. And with this, here's the move. I'm going to take this equation right here. All we have to do is plug that in for ds, like so. And now we have a new equation down here. And how to make sense out of this? Well, I'm gonna make an argument here. By the way, the argument that I'm about to make is importantly, subtly, but still importantly wrong. I'm going to do it on purpose. Commit a little math crime. If you can catch me in my error, please do. Keep it to yourself, though. I want everyone to have the same opportunity to think about it and figure out why this could be wrong. But I'll reveal the mistake on the next page. I'm going to argue that this product, well, capital N and little n, they both point perpendicular to the surface. This product, therefore, perpendicular to the surface and has the same magnitude as capital N. wait a minute, capital N also points in the same direction and has the same magnitude as capital N. Looks like a duck, quacks like a duck. This should be capital N. Okay, now the crime's been committed, right? I will reveal the mistake on the next page. This is my acknowledgement that there's more to say about this. But for the moment, let's set that little math crime aside. I will fess up completely on the next page. What I'd like to do for the moment is let's just go ahead and put one in the win column. What we have here, after all, is a nice, handy formula for computing flux. Everything in terms of the parameterization. See, this is a double integral, right? Pulled back, it's just, the double integral in the parameter space. Let's compute with this formula. Let's see how easy it is to use, and then we'll get into the subtlety again on the next page. Okay. How we doing? Is everybody with me for the moment? So, okay, we've got a vector field given, we've got a surface given. The question says compute the flux. I am going to just use that formula that we just derived. Here's that formula that we just derived. And of course, I'm going to need capital N. And, well, the way we get capital N, first you have to have a parameterization. Notice, all I've done is recognize that my surface is a graph. And so I've used the graph parameterization. You got other options, I suppose, right? But this is going to be the easiest way for this example. So we parameterize. We compute the I wanted to change colors. We compute the appropriate partials. Then we take the cross product, and there's our capital N. So you just do that computation, you compute that capital N, and let's see here, capital N, plug it in. The vector field, here's our vector field. I've just inserted that. Now you would legitimately complain here, wait a second, that doesn't look the same. But do remember, we have to pull back, right? So we're always plugging in, aka pulling back through the parameterization. The parameterization is over there, and notice in the parameterization, this right here says z is s squared plus t squared. So that z, we pull back, aka plug in, that z is s squared plus t squared. What do you think? Everybody happy with that? Questions, feel free. All right, now the last thing to talk about, what's the range of values for s and t? I've got my bounds right here. A super quick little picture, right? So we've got, we've got, it says the part above the unit square. The unit square is down here like this. And we've got our surface. That's, a little hard to draw something like that. We're looking at the part of the paraboloid sitting over that square. Notice on our surface, x and y, I can see exactly what x and y are doing. X and y go between 0 and 1. Okay. So here's the thing. If x and y range between 0 and 1, and if s and t are x and y, then that means that s and t also go from 0 to 1. What do you think? Everybody follow that? Okay, so it's all over with the shouting for this example anyway. We've got, after all, a good old Chapter 5 style double integral, an easy one at that. You got to dot it out, and yeah, it's a polynomial, and you got to keep track of it. But it's a polynomial, world's easiest anti-partials, constant bounds, easy constant bounds, in fact. So I'm going to call this an easy, dot, y'all compute. Everybody happy with that? All right. Okay. So, one thing we've done in the past is we've worried about orientations. And that when you parameterize, you do have to worry about whether you parameterize with the correct orientation. Now, let me remind you, going back, this is, we've gone way back to, I lose track of these numbers. Anyway, I think it's 6.1. This is the section where we talk about vector line integrals for the first time. And we made the observation that, other than the orientation, I'm in the wrong mode. Other than the orientation, how you parameterize kind of doesn't matter, right? But you do have to parameterize with the correct orientation. Otherwise, you're off by a minus sign, right? Because you might, have a windy mountain road that's going up the mountain. Well, yeah, but if you parameterize it backwards, then you're going to compute the amount of work it takes to come down the mountain. Very different amount of work, of course. Okay. Right? Does that make sense? Okay, well, we have a very similar issue in play with surfaces. It's just harder to see. The nice thing about curves, if you parameterize a curve, it's pretty clear just from however you got that parameterization, you can kind of tell which direction that parameterization is going. And it's usually pretty clear, therefore, whether you've parameterized the correct direction. It's hidden when you do surface parameterizations. So, for example, here's a parameterization I might make for some surface over here. And now how do we determine the orientation that this parameterization imposes on our calculation? Well, I got to compute the partials. Right, so these partials depend on the parameterization. Then I got to take their cross product. That also, therefore, depends on the parameterization. Then I've got to compute the normalized unit vector in that same direction. And so that, too, depends on the parameterization, right? This parameterized unit normal, it depends on the parameterization that you wrote down. But I'll bet you that when y'all parameterize surfaces, you're probably not thinking, oh, well, clearly this parameterizes this way or that way. We're just trying to get points on the surface, right? We're just trying to make these points happen. We just don't have convenient intuition for which direction, that way or this way, which direction is that normal vector going to be. But it remains that the question that was given to us had to come with some pre-existing sense of an orientation. And it could have been this way or it could have been this way. That I don't know. Right? But if someone says, hey, compute the flux through a surface, it's got to be an oriented surface. It's not a well-posed question if the question does not, in some way or another, explicitly or implicitly indicate what the orientation is that is the correct positive direction. So we were supposed to hit a certain given orientation. And we wrote down a parameterization that we basically pull out of thin air and get basically a random orientation, therefore, as a result. Everybody see the problem? Right? It's just not good, right? Doesn't make sense. You can't just ignore the fact that we have to orient a certain way. So again, it's kind of the same as last time. There's two different ways to do it, and if you do it wrong, you've got to fix it with a minus sign. Right? That's this theorem down here. So, okay, well, same here. And this is the little math crime that I committed on the previous page. On the previous page, I conflated these two. We started off with an expression that came from the statement of the question. Right? That little n in green is the orientation unit normal. That comes as part of the statement of the question. Again, either explicitly or implicitly. And then we wrote down a parameterization and blah, 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 lots of calculations, and implicitly, kind of in subtext, just assumed that all away and said, well, here's our parameterized unit normal. That's hidden inside of the capital. And so when I claim that these are obviously equal because looks like a duck and quacks like a duck, right? I was ignoring the fact that there are, in fact, two different directions through the surface. We are supposed to pick one of them specifically, and we basically picked randomly instead. So assuming that those two directions are the same is the problem. That's the little math crime. That's what this asterisk is here. Those two things may or may not be the same. How we doing? Okay. All right, so the good news, just like with vector line integrals, the way we deal with this, the way we deal with the fact that, there's a plus or minus, I don't know, that we're going to have to insert, basically, don't worry about it for the first half of your calculation, and then once it becomes clear which way you've done it, see if you did it right or you did it wrong, and if you did it wrong, fix it very easily with a minus sign. Okay, so let's see this in action. By the way, let's look back to before we go ahead. Let's look back at this example that we did here. I don't know if anybody noticed. I was trying to be dramatic about it, but you notice how I didn't make any mention of this word upward as we discussed this example? I just kind of glossed right over that, didn't I? You're not allowed to just gloss right over things, right? So I should have addressed in this work here the fact that this question says we want upward flux. We've got this surface. I want to consider positive through the surface to be the direction that's going upward through the surface. Now I can see that I got it right because once I get down to this capital N vector, I can see that indeed that is, it's not straight up, but it's, it's the upward direction, not the corresponding downward direction. Is that cool? We got lucky with this one. But it could have gone the other way. And so this next example is practically the same example, almost exactly the same example. This time, though, given as oriented downward. Same vector field, same surface, same unit square, all the same. This time, though, oriented downward. Okay, so now, did I get it right or did I get it wrong? Well, I chose this parameterization, kind of hard to tell. Is that upward or downward? It was hard to tell at a glance, right? And I take these partials, are they upward or down? I can't tell how the resulting orientation is, but once I get to the capital N vector, now I can tell, right? This capital N vector, clearly, just like in the previous example, using the same parameterization, still oriented upward, but I was supposed to orient it downward. So I blew it, right? We messed up, right? This downward is what I was supposed to get. Upward is what I accidentally got. I oriented wrong. Yep.
You find big N by RS cross RT, right?
Yep. Yep.
Does it matter which way
it does.
you cross it?
It does. Now, of course it does, right? Cross product is anti-commutative, right? When we write down this formula, R is a function of two parameters, and how you write it down implies which one you're considering to be first, right? So in some sense, that's part of how you write it down as a parameterization. And then you're supposed to do the cross product correspondingly in the same order, right? Yes?
On that note, because it's anti-commutative, if you had like T then S.
Yeah, that would be a different parameterization. Yeah, because I would be considering R then as a function of T and S instead of S and T. And so it effectively, other than, the labels, it's morally a different parameterization. Yeah. Does that make sense? Yeah. Okay, so we blew it. Now, do we have to start all over? No. we know exactly what we did wrong, and we know exactly the problem that's going to create, and we know how to fix it. What we did wrong is we parameterized the wrong way. What it's going to do is it's going to insert an inappropriate minus sign, and we're going to fix it by inserting a second inappropriate minus sign that will cancel, right? And so there's nothing to it. I mean, don't worry about it. Just once you've identified that you got it wrong, stick in your minus sign and proceed. That makes sense to everybody? Okay. So there's two things that are subtle about this that you do have to keep in mind, and this is important. The first is you have to remember to check, right? Your notification that you're responsible for the orientation that's given is simply that it is given like this. Right? The fact that this says downward means you're in charge, you're responsible for making sure that you respect that orientation. So you have to remember to check because you're responsible if you didn't do it right. And depending on how quibbly your grader is, even in a case like this, where we did get it right, but you notice how nothing that's written on the page here gives any indication that whoever wrote this, it's me of course, whoever wrote this, did the person who wrote this know? Did they realize? Or did they just get lucky? Right? So the prudent thing to do, even on this one, would be, now look how easy this is to do. You do something like that, boom, it's perfectly clear what that means. Perfectly clear to the grader that you recognized that you're supposed to orient upward. You're confirming that you did orient upward. Right? Now you don't have to worry about a quibbly grader. So I encourage this. I encourage you to, go ahead and remove all doubt. And by the way, your grader will appreciate this. Your grader will think, oh, yeah, this student knows what they're doing, and will probably, I'm just thinking about psychology at this point, they'll probably just be kind of rounding in your favor for the whole rest of the question. That's also a good thing, right? Okay. All right. Okay, now, so the first big important thing, make sure that you check. You have to remember to do that. The second important thing, when you insert the minus sign, you have to insert the minus sign in the correct place. Now let me explain where I've put it there is the correct place. We were asked to orient downward, so this, whoops, I'm in the wrong mode. When we've been asked to compute flux, right, says right here that's supposed to be downward, so this capital phi right here, the assumption of this phi is that it is per the statement of the question, and this means downward oriented. DS also tracks with the given orientation. Let me just remind you, going back to here. Yeah, here we go. The DS vector, right? The orientation is the given surface orientation. Let's see here. This next line is the one that depends on the parameterization. As you can see, this next line, the orientation is sort of hidden inside of that capital N vector. That capital N came from the arbitrarily chosen orientation, parameterization. I just kind of pulled out of thin air. Okay, so that's where the thing has to go, right? This extra minus sign is the way to acknowledge that the green orientation and the blue orientation are opposites, and so we fix it with a minus sign. Does that make sense? Now let me show you what happens if you put this in the wrong place. Right? Now just for the drama of it all. Again, this is just further calculation of the blue. What if I were to not put the minus sign here? What if I were to not do that at all? And what I did instead was I put the minus sign there. there are now 2 false statements on the page. Right, and keep in mind, it's not about the answer that you get at the end of the, putting a box down at the, bottom of the page. It's not about the answer. It's about the reasoning, right? And right now we have 2 false statements on the page. For one thing, this equation here says that the green and the blue are the same. They're not. So that is not true. Right? And then, this statement right here, this equal sign, says that the blue is the negative of the blue, which it is not. Right? Does everybody see what I mean there? Right? So it's, this seems fussy, right? But this is an unavoidable consequence of, look, if we are in fact caring about reasoning and caring about communicating mathematical reasoning, in some reasonably appropriate sense, then you have to worry about this. And so please, please, please do make sure that you insert those minus signs at the place where they kind of have to be to avoid this problem. Okay. Everybody all right? By the way, y'all are very welcome to open windows if you prefer. I see some people fanning themselves. I'm sorry about that. So whatever y'all want to do is totally fine. Okay. Moving along. All right. There is a little bit of point of language to discuss on this. So when you're stating a question, you want to make sure that the person who's going to answer the question has the information that they really need, but you don't want to do half of the problem for them, right? And if you're asking the question for someone else to work out, you might not even know how to answer the question. So, point being, as we ask questions, we very often won't say things exactly right. So, for example, looking at these 2 possible orientations for this paraboloid. Oh, come on, let's see here. There's a paraboloid. There are 2 orientations. There's this one here, indicated by these green normal vectors, and then there's this one here, indicated by these blue normal vectors. Those are 2 possible orientations. And I suppose maybe I could describe that I want the green orientation, not the blue orientation, by actually solving for and writing the explicit formula for these green normal vectors. Well, I want y'all to do that, right? That's part of the solution. So I would like to be able to distinguish the green from the blue without having to write down the explicit exact formula. And so the way we do that is we use fairly sloppy language like upward and downward. Now, are those green vectors, are they all exactly straight up? No. They're, almost all of them are not exactly straight up. Well, yeah, right, of course. Right? But if I say oriented upward, and if you know that these are the 2 options, I don't think there's any ambiguity here, right? Obviously, the green vectors are all at least somewhat upward and not in any sense downward. The blue vectors are all at least somewhat downward and not in any sense upward. So saying upward is is unambiguous. And that's the point, right? For the purposes of stating the question, saying, oriented upward gives you all the information that you need to answer the question. Completely clearly describes you want the green orientation, not the blue one. Even though, technically, upward, if you had to pick a direction that we would call upward, these green vectors aren't yet. Everybody see the situation there? It's kind of how it has to be. So, please don't make the mistake, and I do see this, less often these days. As usual, the bigger a deal I make out of it, the less I see this mistake. But I still will see a certain amount of students seeing the word upward and then just think, okay, well that means my little n is 0, 0, 1. And that's just wrong. That's not what the word upward means in this context. In this context, it just means the green one, not the blue one. That, okay, everybody see what the situation is? And, all right. Be advised, likewise. Here's another scenario we might need to worry about. Suppose we're looking at a sphere. You know what, this is going to be too much mess. The two possible orientations on the sphere are, again, I'm going to color that green one, and then likewise there's the sort of the, what you might call the blue one here. And what language would we use to distinguish between these? Well, don't say upward versus downward. Both of those orientations have some vectors that are somewhat upward, and both of those orientations have some vectors that are somewhat downward. So the upward and downward language is absolutely wildly unacceptable for that surface. Doesn't do the job. It's not unambiguous. It's just doesn't do the job, right? So what do we do instead? We say inward versus outward totally distinguishes the green from the blue. No problem. Question's perfectly meaningful and clear at that point. So then use that language. That make sense? So you have to tailor your language to the surface, to sort of the geometry of the situation you're looking at. And likewise, sort of on the flip side, when you're reading a question, you have to interpret from the given language appropriate to that geometry. Okay. Moving along. All right, so sometimes you get lucky. It's really nice when this happens. And by the way, just for just to make the analogy continue, recall this was one of the next things we talked about for vector line integrals. For vector line integrals, we had this nice example of, hey, wow, just keep your eye on that geometry, because sometimes you get lucky and the geometry makes a otherwise difficult question just disappear in a puff of smoke. So that's what's going to happen here. Now, it's a kind of it's a different scenario. Here we're computing a flux, but let's see here. The sphere has this feature, specifically sphere centered at the origin, has this feature that all of the position vectors are perpendicular to the surface. Gotta love spheres. Right? Spheres centered at the origin are the only surfaces that have this feature, that the position vectors are always perpendicular to the surface. And that being the case, if you want a unit vector perpendicular to the surface, then you just divide the position vector by its own magnitude. Boom, now you have a unit vector, and there you go. Right, so very convenient to write that down, and there you go. Oh, whoops, wrong color. I keep missing the thing. There you go. And then we already have the vector field already given to us, and then you notice that dot product is 0. Poof, done. We walk away. Didn't have to parameterize. By the way, how would we parameterize this surface? Well, it's a sphere. I'd probably use the spherical graph parameterization, sines and cosines everywhere. Got to plug those into the vector field, sines and cosines everywhere. Now, when you do that dot product out, yeah, it will be 0, but after doing a non-trivial amount of inconvenient trig. Does that make sense? All right, so eyes open, right? Be on the lookout. Here's another example. And again, works out really nicely. We have a surface given. It's part of this plane, y equals 3. And now, it's not the whole plane. It's just that part of it there. Just the sort of the dark green part. And I'm a little worried already because specifically that dark green part of the plane that is my surface is described with a quartic equation, and I've got, flashes of, oh my God, am I going to be dealing with fourth roots here, right? That seems like it could be really bad. Well, there's a couple of nice freebies that we get. For one thing, just because we're looking at the plane y equals 3, I immediately know that's my normal vector. Okay, I do have to worry about orientation. Well, it says in the positive y direction. This is the positive y direction. The alternative would be the negative y direction, so this is positive. Good, right? So there's our normal vector, and again, we get to just immediately write that down. Lucky geometry. Is that cool? Everybody happy? And now 2/3 of the problem just disappeared because there are three coordinates here, and 2 of them get multiplied by 0. So that's a pretty awesome thing. Here's the other big win. The other big win. Let's see. How am I going to do this? Yeah, I guess I'll keep that there. From the same fact that y is equal to 3, that means that the second coordinate of my vector field is always 0. Now, it just happens to be the case, and sure is convenient, and something to be on the lookout for. Again, if you know something nice about one of your variables, and that applies to your entire surface, yeah, plug that on in. Right, all good. So yet more zeros, and of course I have deliberately arranged it to where these zeros would complement each other perfectly, and again the dot product is immediately 0 and we win. Well, I'm not saying it'll always work out that way, but in this kind of thing you'd be surprised how often this can be very helpful at least. What do you think? Let's see how these work out. Okay. Okie dokie. Okay, let's see here. The next thing, coordinate surface integrals. And by the way, looking back to the vector line integrals discussion, right after the lucky geometry, very next thing we did was we talked about coordinate line integrals, which basically is just a matter of taking our pre-existing formulas, writing it out in coordinates, plugging that into our formula, and noticing we have a new notation that's kind of bulky, not particularly intuitively satisfying. Don't really like it in this context, but it is in common use. You are going to see it, and it's important to know what to do with it when you do see it. And by the way, cultural note, very, very important math looks a lot like this. Just, FYI. So, okay, the exact same story happens here. Right? We take our existing formulas. We already had all that's, old news. We plug in my coordinates. Got to crank out this cross product. By the way, I made a reference last week at some point about how that cross product works out like this, and I didn't tell you. I didn't tell you why, in some sense, it should work out this way, why it's natural and, I don't want to say obvious, but why it is appropriate and really ultimately to be expected that these are two-dimensional change of variables stretching factors. But we are going to make use of the fact that they are two-dimensional change of variables stretching factors on the next line here, because what would be the natural thing to call that? And I think dy dz makes loads of sense, if only just from the notation. Right? Now, is there a geometrically justifiable motivation for calling them dy dz? Absolutely. Come to my office hours anytime. It's going to take 15 or 20 minutes, but we can talk through why, in fact, this really does make loads of sense. You don't need to. You don't have to. But if you're curious, feel free. What we're going to do here is just take advantage of the fact that, that's the wrong word. We're going to see the consequences of that equaling that. Namely, of ds. Whoops, I missed. ds being rewritable in terms of these, let's see what we call these coordinate surface differentials. Because we can just plug that in here. Right? Seems like, I mean, this is why, if I can justify calling this ds, then I can justify plugging it in. And as usual, if your vector field has some certain coordinates, you plug that in too, and then you write out the dot product, and we've got ourselves another new notation for vector surface integrals. Pretty analogous to what happened with vector line integrals. So we call these coordinate surface integrals. And again, it's bulky. And again, it's kind of unintuitive, right? As to why would I write this and why does this make sense? It's not it doesn't leap off the page at you. And again, two things that you should know. One is, there are pretty great things about this notation, in fact. We're not going to talk about them in this course, so you just have to take my word for it, right? But there are some really powerful things that you can do with this. This is what differential two forms look like, right? And again, powerful tools, and that's what allowed for proving certain big theorems and resolving various, mysteries, little mathematical mysteries that arguably were mysteries for 100 years. So very important stuff. But how does it affect you, other than it's good to be sort of culturally aware of big points? The way it affects you is that whether we like it or not, you are going to see stuff like this. And not just in Math219, right? You're going to see this out in the wild, right? On the street. Engineering classes, stuff like that. And when you do, I suggest that you just recall, okay, this is just an alternative notation for a vector surface integral. By the way, sometimes we call those flux integrals because that's the motivating metaphor. And in particular, not only can you realize that what it represents, but given that these, in that order, represent ds, you can infer that these integrands are just telling you what your vector field is. What do you think? Everybody see how that works? So that's what I would encourage. I mean, when I see something like this, in a Math219 type context, honestly, the very first thing that I do is I take these formulas and I just say, okay, all right, this is what they meant. It's flux of this vector field. All right. Okay, so I guess I ended up doing this page after all. Oh well. Okay, next, symmetry theorems. And again, of course that's next. That was what was next with vector line integrals. The analogy is very strong. And let's see here. So symmetry theorems. Golly, this is so familiar looking. In fact, I think when I wrote this, I probably copy-pasted the whole thing from chapter 6 and then, changed a couple of details appropriate to the situation. Right? It's really, really very similar. If you have an odd integrand on a symmetric domain, the integral is equal to 0. By symmetry, you do of course need both of these conditions to hold, and you have to use the same plane for both. So, I hope that sounds familiar, right? That's like our 4th or 5th time to write down an odd symmetry theorem of this kind of sort of structure. Same basic ideas for all of them. And just like with line integrals, this is for scalar surface integrals only. Just like, remember with line integrals, It doesn't work for vector line integrals, and likewise, it doesn't work for vector surface integrals either. For vector surface integrals, your integrand being odd doesn't do anything. It doesn't work. There is no odd symmetry theorem for vector surface integrals. And the reason why, again, pretty believable, because if you look at the ds, right, we can just directly see that these normal vectors on, sort of opposite pieces of the surface, they're not the same. Not only are they not the same, they're not negatives of each other, nothing. They're just different. So the theorem crashes and burns. So please, please, please be very, very careful about this and don't try to apply an odd symmetry theorem to a vector surface integral. Okay, last thing we're going to do. So I've been deliberately developing vector surface integrals kind of in parallel with the way we develop vector line integrals. They are actually pretty analogous. I think there's value in seeing that, so I like to develop them in service to that point. Let me go a little deeper on how strong that analogy is. I think this is a fun exercise. And by the way, why? Because both line integrals and surface integrals, both of them, are integrals of differential forms. Vector line integrals are integrals of differential 1 forms. Vector surface integrals are integrals of differential 2 forms. They are literally the same construction applied to different circumstances. So of course they're analogous. They come from the same general construction. So how are we going to see that? Of course, we're not going to do differential forms in this class. The way we're going to see it is just by observing directly some of these analogies. So, for example, we parameterize a curve, we parameterize a surface. Let's see, we take the appropriate derivative. To get the velocity vector, we take a couple of partial derivatives and then a cross product. To get the capital N vector. And among these formulas that we've developed over the last several lectures, right, all old news, all these formulas, all old news. Among all those formulas, notice that the V vector and the N vector, capital N vector, sit in analogous places. And likewise, the unit tangent vector, the unit normal vector sit in analogous places. And the vector differentials, the dr vector and the ds vector sit in analogous places. And the ds, I need a highlighter mode. The ds, little ds scalar representing length, and the d big S scalar representing area, those sit in analogous places in those formulas. Right, so these kinds of integrals, I mean, they're different things. They come from different physical applications. They apply in geometrically different circumstances. One's on a curve, the other's on a surface. They're different. Yeah, of course, very different. But look at the strength of the analogy. You can see it's the same story in a different geometric context. It's like we used vector line integrals as a template almost. And just said, okay, well, same stuff, one dimension higher. The analogy is that strong. Right? So I think this is a really, really underappreciated point about vector calculus. Within multivariable calculus classes, at the undergraduate level, how strongly analogous these constructions are, I think, is shocking. I mean, this is a real jaw dropper for me. right? And doesn't get mentioned very much. How does this affect y'all? Well, in two ways. One, against cultural point, right? So y'all now know, at least have seen kind of, glimpses into some really sophisticated points about this stuff that most students don't ever see, right? But more practically, more rubber meets the road. Because of how strong this analogy is, it's kind of like once you understand this, you understand the sort of the pattern. You don't have to relearn a whole new pattern. It's the same pattern, right? So what you understand about vector line integrals should help you solidify an understanding of vector surface integrals by recognizing the pattern. Perfect timing. See y'all later. Have a good one, and see you on Wednesday.